my talk today, as Lavanya said, is about learning to, you know, basically learning deep reinforcement learning and sort of the path that I took through this, and sort of some of the pain points of trying to get some of these algorithms to work. And I started doing this about 2 months ago. And in this talk, the topics that I'm going to cover, they're mostly, I guess, they're kind of beginnerish, but I'm going to talk about what deep reinforcement learning is, or rather, what reinforcement learning is, and then sort of how we involve a neural network. And so, to that end, I'm going to discuss a sort of the classical reinforcement learning algorithm called Q-learning, as well as this variant that uses a neural net. And then I'm also kind of talk a little bit about exploration, which is an important topic in reinforcement learning, and how sort of exploration became kind of a difficult thing in one of the problems that I was working on for my channel, where I was trying to train a model to play the game Snake. A little bit about me and some shameless plugs. So I'm a senior computer vision engineer at Simbe Robotics. We build a robot that um, sort of scans shelving in retail stores, something that's become extremely relevant in the past few weeks, and then tells the store employees when things are out of stock. And I sort of been with them from roughly the very beginning, soon after they got their first sort of round of funding. And I've been working on their computer vision stack and sort of building that out. I also recently started, well, about a year ago, started a YouTube channel by the name of Jack of Some. And as was said in my introduction, I make videos. I started with making videos about text editors. I use Spacemacs, and I really like it. And so there weren't enough tutorials, and I started making videos. And then since then, I've been making videos about Python and reinforcement learning in general. I also have a Twitter. Come find me. I'll probably be yelling about something related to Python there. So my reinforcement learning work, a lot of it actually is tied to my channel, because I don't do this professionally. I do, I do deep learning, and but mostly it's in the context of computer vision and having to do with object segmentation, object detection, and things like OCR. I wanted to learn reinforcement learning for a long time, and I never got an opportunity to do that at work. So instead, I decided to tie it to my channel, and I decided that I would do videos and live streams about reinforcement learning, and in that process, I will sort of maybe grow my channel, and also I'll learn this new thing. So I did this live stream, and the point of the live stream was to sort of apply basic Q learning to a very simple maze solving problem that you can see on the upper right here. Sort of do it from scratch and see how that goes. And that ended up being fairly well received, even though it's like ridiculously long. So let's talk a little bit about what reinforcement learning is for those that might not know. The typical classical example that's given of the structure of what reinforcement learning is, you have some agent, so some thing, that you can consider that as being a player in a video game. That can be a robot. There's a number of different ways to imagine what the agent is. And then there's some environment. So that could be the level of the video game. That could be the physical environment that a robot resides in. Any number of things. And we'll see that sometimes the agent actually needs to be considered as part of the environment, because it's a significant piece in that environment. The agent has, being it's an agent, it has some agency. It can do some actions. So given, there are a few things that it can do. In doing so, it's going to change the environment, and the environment is going to respond to it by giving it some sort of a reward. And the reward signal is there to, it's more for learning, less so, I think, for the actual, when you actually run the agent. But the reward signal is there so that the environment can tell the agent if what it's doing is good or not. So a simple example might be, a bump sensor on a robot, where if it runs into a wall, the reward is -1, because, hey, you should not be running into a wall. And the point there is that then by setting up some very simple rules and very simple rewards, we can get like a neural net, or just a general function approximator, to learn how to take the best actions in an environment, without actually teaching it, without actually creating like some sort of a code that says, if this, do that. We just train a function, and then that function is able to decide the best way to navigate the environment. Now, as the agent takes actions, there's also state changes. So like in the case of a robot, if the action is, you know, move a finger, then the state changes, the finger has been moved and it's in a new location. And then there's sort of terminal states. In the case of a video game, you can think of this as a character dying. And in the case of a robot, it could be an action that's just unacceptable, like, again, bumping into a wall. And in that case, you can say, hey, the test has ended. You got a big negative reward. Don't do this again. And then the hope is that the agent can learn to avoid that. To make this a little bit more concrete, and it's not exactly concrete because we're still talking about a virtual agent. The benchmark example that I've been working with for some time to sort of learn reinforcement learning has been the game of Snake. And as it turns out, I picked the game of Snake because I thought it was going to be easy, but it's actually supremely difficult. And I'll talk about why in a second. But the agent in this case is the head of the snake. I like to think the agent as just being the head because the body of the snake is actually the environment. And the head can actually collide with the body and receive a negative reward, essentially death in this case. The actions that are possible are going up, going down, going left, and going right. And then the reward signals are for eating the food, the snake gets a +1. For, you know, if it dies by running into the walls of the environment or by running into itself, it gets a -1. And then if it exists and doesn't do anything for a frame other than just moving, then it just gets pain because all existence is pain. That translates to a very small negative reward. This is something that's very commonly done in reinforcement learning to sort of teach the agent that it doesn't just need to accomplish the action, it needs to accomplish it fast. Otherwise, it'll get this sort of constant small ticking negative reward. So enter the Q-learning algorithm. The Q-learning algorithm is meant to essentially help you learn a function. Classically, this function is often a table, but then the more contemporary versions of this function are neural nets. And the function's job is very simple. You are given a state, and going back to this example, the state in this case could be, you know, the structure of the snake or the image of the game itself. And then it's supposed to predict basically a vector that says, hey, if you take action number 1, then the max reward that you would get in this environment or in this episode is going to be some number. And then if you take A2, the max reward would be some number, etc. So using, and this is supposed to be, when I say max reward, this is supposed to be like encountering both the reward that it'll get immediately as well as the reward that it would get in the future. So the point here is that by just evaluating this vector and looking at the highest reward value, that tells you the best action. So you don't have to do any kind of model-based prediction. You can if you want to, but, you know, standard control systems used to do a lot of model-based prediction. But in this case, you don't have to do that, because once you've trained this function and once it's able to predict these Q values correctly, you can simply just pick the row that gives you the max Q value and then take that action and just keep going forward. So this process of making a decision becomes constant time. So like I said, the future needs to be considered. So as an example, let's consider, again, the game of Snake. In this case, the snake somehow got itself into this predicament. And, you know, that could have happened through random actions. Maybe it's just sort of exploring the environment in order to learn. And it's gotten to a point where going into one direction, it'll get food, but then immediately after that, it'll die. So let's, I wrote that down. So going into the right, it'll get, you know, in one time step, it'll get food. And that's a +1. You know, that's a good action. But then in step 2, it's going to die. There's no way out of this. There's no escape. So, you know, it looks like from the perspective of a model that's just sort of greedily trying to find the next best reward, this looks like maybe a good direction to go. But if you consider the future, it's not a good direction to go. On the other hand, if you go left, that's actually immediately bad, right? So from a greedy standpoint, if you go left, it's just pain. You don't get any reward. You just get like a -0.001. And then second time step, as you go further left, it's also -0.001. And we just keep going on. And maybe after like 25 time steps, finally it gets to eat food. But that's good because it's not dead, right? So what we're trying to do in terms of creating quote unquote an intelligence is to learn a function that can make this decision of going left in this case rather than going right, even though the immediate reward is to the right. So here I've just written out the reward, the actual Q values that you would expect in these cases. This is not the actual correct Q value. It's just looking at um, it's just the case if you only have one additional fruit and the game ends. The value would actually be higher for a normal game of Snake. So the learning in this case, how we actually learn that function, how we fit it, that's done through something called the Bellman equation. And the Bellman equation, sorry for throwing this much math here. I was trying to keep things simple, but I think I kind of have to talk about it. I'm not going to necessarily talk about the context of how the Bellman equation comes to be. We can just sort of take it on faith at the moment. But the Bellman equation says, hey, by definition, the Q value of your agent being in some state at time t and having taken some action at time t is going to be equal to the reward that action got it for that one step, plus whatever the maximum that you can expect through taking any actions for the future state. Right? So this is a recursive relationship. And you can sort of expand this right point out all the way until the end of the episode or some time horizon that you've chosen, and get sort of what the actual Q value is supposed to be. So we can use this for learning by, let's say, having a table over the states and actions, because it's a two variable function. And then you can sort of start that table randomly or with zeros. And then anytime you observe the sort of the reward from a particular state, you can kind of start from the end and work your way back to slowly update and slowly increment the cells of the Q table to sort of try to learn what the Q value is actually supposed to be. And so, as an example, at the end of the live stream, I was able to show that for a very, very simple problem where you're trying to solve a maze and only solve that one particular maze, you can sort of randomly explore this entire environment, and then as it starts to be able to get to the end here, it's the reward is sort of going to propagate back through this path. And as you look at the Q table, which unfortunately I'm not showing here, it starts to show that taking the action here gives you an eventual reward of 1, and taking the action here gives you an eventual reward of 1, and then going into any of these obstacles gives you a -1 immediately. So this works really well when you have a small number of states, which in this case I believe was 64 states, and a small number of actions. But as you sort of make things more complex, so like what happens when the input is really complex, you have this image. In this case, this image was a 320 by 320 image, I think. So that's like, if you consider sort of that just turns into a lot of different combinations and a really, really large state space. And using a table to fit this isn't really feasible. And so instead we use neural nets to approximate that function. Note that neural nets don't have to be, they're not the only way to do this. Any arbitrary function approximator can work with Q-learning. Neural nets are just the best ones we have right now. So as an example of how this ends up working, I'm showing a slide here from I believe this was the Nature paper from DeepMind, where they were sort of explaining the system that they built to play Atari games at a superhuman level. And the input here is the same as what I said for Snake, so it's a bunch of pixels, and then we have a convolutional neural net with some ReLU activations, and then some fully connected layers at the end, and then there's some number of inputs. In this case, various joystick directions, and then pressing the button, and then pressing the button with various joystick directions. And instead of using a Q table, now we can use the same Bellman equation to train this neural net, and the loss function now has sort of reward plus this maximum of the Q value minus the observed Q value from the current state. And so this maximum of the Q value then comes from the neural net, and this Q value comes from the observation. And using this approach, and there's a bit of nuance here that I'm not going to cover in this presentation because it'll take much longer. But using this, we can construct a mean squared error loss and then fit a neural net. So going back to sort of when I was trying to do this to solve the snake problem, I was trying to do this in Keras, and this requires a custom loss function. It has a weird target that you need to fit to because if we go back to this equation, we need to take a maximum of this Q value over a particular action, and doing that in Keras becomes really, really weird. And so this was not a fun experience when I was trying to do it, because I found myself going into sort of doing things in a really weird way in Keras that I didn't quite like. Um, Here's I'm sort of trying to show how that works. So like the model here is the actual model that I'm trying to train, but then because of how the Keras API is laid out, if you're just trying to use sort of the main Keras API, you have to wrap it in a new model where the inputs are now not just the image, but also this target value and the mask, and then you sort of just pass those through the model and then construct your custom loss function using all of those pieces as being present. And that was not particularly nice. And then in addition to that, when I was trying to research this, I ended up running into this problem where, and I hate to pick on this article, but this seemed to be the most clear article. And then I later found out that the formulation that they had presented was totally ignoring sort of the nuance that I showed here in the Bellman equation that for constructing the loss. And so it worked fine for small problems. And I was trying to work on this with maze solving on a small grid, and it worked fine. But anytime I went to a bigger problem, it sort of fell apart because it wasn't following the Bellman equation correctly. So as I was sort of doing this exploration, trying to find easier ways to do this, I landed on this library called Keras RL, and it's a really well put together library. And I highly recommend anybody that's starting out in reinforcement learning that wants to use Keras and not necessarily go into the nitty gritty of things, that you should check this out. But oh, sorry, there's no but yet. This ended up working reasonably well for me. I constructed this the snake benchmark problem, and this is from training, but it was just sort of out of the box using their DQN implementation. I was able to get it to work reasonably well. The problem is that Keras RL has a few issues. It is at the moment, if you try to install it from source, I believe it is broken. Something to do with an integration that was added, and as far as I can tell, it's not currently being actively maintained. That might change in the future. And then it also focuses only on the Q learning related algorithms. There's an entire other class of RL algorithms called policy gradient, and Keras RL currently does not support that. And I suspect that it would get really hairy supporting all of those in Keras, just if you're just using the old Keras API. Positive thing though, through Keras RL, I got my first introduction to weights and biases, because that's integrated into Keras RL, and then I sort of started looking into it, and it's been really great for me since. So moving forward, I sort of abandoned Keras RL as well, and went the route of sort of trying to implement these things by myself from using the new TensorFlow 2 API. And that actually ended up being much nicer. Now, I know I've sort of thrown up a bunch of code here, and it actually does take a little bit of time to go through this and sort of correlate it with the equation. But the nice thing here is that I no longer have to create like a dummy model that has pass-through inputs. I can just create this train function and pass in sort of everything as sort of it comes from the simulated environment, and then go through sort of a series of functions and construct my loss that way, and then just sort of use an optimizer to do back propagation through that. So that's the other thing, is like, if you're willing to get your hands dirty a little bit, then don't sort of go with an existing framework or something like that. Just try to implement these things from scratch, and consider using something like PyTorch or TensorFlow 2, because they're really, really nice APIs now, and they form these they fit to these problems really well. So around this time, now the video that I was showing before of the snake exploring, it never really could do better than what I was showing there. And one of the reasons for that was that exploration is, I'll talk a little bit about what this is, and then I'll get back into how this connects to the snake problem. So typically when you're using deep Q learning, the standard way of doing exploration is called epsilon greedy. And epsilon greedy essentially says, in the beginning, the model has no idea what to do. So at the start of the training time, because we can't, we have absolutely no idea what should be done, we'll just do something random. So in the case of snake, we'll take one random direction and move to that. And every time step, we're just going to do something random and keep track of, all the state changes and all the rewards and everything, and then start training on that. And then the idea is, it's not necessarily very easy to evaluate if your model has how well your model has learned. So we're just gonna sort of create some time horizon, let's say like 1,000,000 steps in the environment or something like that. And then over that time horizon, we're slowly gonna decrease the amount of randomness, or what's called epsilon, until it becomes really, really small. It never goes to zero, because you never want to create a situation where the model can't explore anymore, because it's always following its current best strategy. And so usually it asymptotically reaches some very small value, like 1% or something like that. So yeah, at the beginning you start very random, and then at the end we get sort of not very random. There's a problem with that, and this is not necessarily like there's a number of problems with it, but in many environments this problem doesn't show up. But in the game of Snake, it shows up very, very clearly, which is that even 1% randomness, or even smaller than that, depending on if the game of Snake is really large, it's too random in the late game. And the reason for that is I'm showing here a 6x6 game of Snake, and by the time that it's gotten here, it's gone through maybe 200 moves. And I did some sort of back of the envelope math to see, if the randomness percentage was like 1%, then what is the chance that by the time it reaches this particular scenario, what is the chance that it would have taken at least one move that would have killed it? And there was a 63% chance of that. And so this percentage becomes higher and higher as we make the game of Snake bigger, and as it sort of plays longer and longer through this game. So epsilon greedy maybe might work for a really, really small epsilon value, but it'll probably take a very, very long time. And maybe it's not necessarily the best way to do exploration for Snake. So one of the approaches that's often used in this scenario is, what if we can reinterpret the Q values as probabilities? So in this case, going back to the situation that I was showing before, we have an expected Q value of 0 if the snake goes this direction, and then -1 for up and down, and then 0.975 for going left. We can softmax this, and that gives us a probability distribution where it's sort of reinterpreting those values as, what is the probability that taking this is a good action. And of course, this is not perfect, because that creates a 10% chance of going up here and 10% chance of going down here, both of which would cause immediate death. But now the total chance that it will take a good action in this scenario, which is, kind of fairly in late game, is relatively high. It's like 60%. So we can just sample from this distribution and use that for exploration. But there's actually things that are a little bit better than this, because as the snake learns more and more, it's going to know that the Q value of moving in this left direction is not 0.975. It's actually much higher than that. The expected reward of going here is much higher, because the game actually continues on, and the snake can sort of continue to eat more and more. So if we use this and softmax that, then the actual probability distribution is very, very heavily weighted now towards the snake going left in this case, not going right, up, or down, because the probabilities there are just exceedingly small. So as the snake learns more and more, and as the Q values become larger and larger in this scenario, this approach, which is called Boltzmann exploration, becomes much, much better. So as an example of that, using this approach with the DQN, the snake agent is now able to almost win a 10x10 game. I didn't continue training this, because I eventually moved on to policy gradients, but this is sort of an example game that I was able to train with Boltzmann exploration. And this is something that I was never able to do this well with epsilon greedy. And now we have an abrupt ending, because my original plan for this presentation was to cover more ground, but I realized that just covering Q learning was actually going to take much longer. I'm going to talk a little bit about, before I talk about the resources, I want to talk about how weights and biases has helped me do some of this experimentation. So this is one of the dashboards that I was using to track when I was working through the game of Snake. And one of the things that I really, really like in weights and biases over something like TensorFlow is that naming the runs is really, really straightforward, and you can change these after the fact. And then sort of looking at all this data is really, really easy across different runs. So I was having to keep track of like, hey, I beat a 4x4 game and a 6x6 game. I kind of want to see how those behaved versus a 10x10 game. So being able to sort of have access to this on the fly on my phone was very, very helpful through this process, and it continues to be helpful. A little bit about resources for those that might be interested in learning more about reinforcement learning. David Silver's course is really useful. It's on YouTube. It's free. It's something lectures that he gave in 2015 at DeepMind. One of the things that I would recommend if you're going to watch this class is to start doing some experimentation on your own while or before you're watching them. And what that'll do is it'll create a nice feedback where you will have a much better idea of what he's talking about because you've sort of already struggled with it. Another resource that's really useful is this series of repositories called RL Adventure from this GitHub account, Higgsfield. And RL Adventure contains mostly DQN related stuff, and then RL Adventure 2 contains policy gradient related stuff, which is something that I couldn't talk about in this presentation. A third really useful resource, if you're using PyTorch, which is what I'm using now, I kind of moved on from TensorFlow 2, is Ilya Kostrakov's repository, where he's implementing four policy gradient methods that are sort of the more modern algorithms that are used in reinforcement learning right now. And it's really well laid out. The code is really easy to understand. And sort of if you're looking to check out the guts of some of these algorithms, it's a really good repository for that. And that's all I got. I don't have a conclusion slide. So if there's any questions, I'll take those now.
That was really good. Thank you. I see one question from Piyush. He asks, what kind of environments can you apply reinforcement learning to? And is it always supposed to be a gaming environment, or are there other domains where you could apply reinforcement learning?
No, reinforcement learning does not always, I'm going to go to a less busy slide. It's not, games are just the easiest place that we can sort of study and research reinforcement learning. The actual field is really old, and it's actually been applied a lot in things like finance, but it's never been applied in finance is real world, but I was going to say it's never been applied in something real world, quote unquote. In like, let's say robotics or something like that, for stuff like that, it's relatively new, and it gets this bad perception that, oh, people are just playing games with it. Like, oh yeah, of course, fine, you beat the game of Go, but what does that mean in real world terms? Or now they're playing StarCraft and Dota at a superhuman level with reinforcement learning, and people kind of roll their eyes at those news because it's like, why are we wasting time doing this? Games are for people to play. But it's just an abstraction, right? It's kind of like how researchers in the 60s and 70s were always working on the inverse pendulum problem and the problem of like balancing a stick on your finger and solving that with mathematics. And that sounds like a silly problem, but it was actually really important for rockets and a number of other things that have more recently become relevant. So games are just a useful abstraction. Outside of games, like I said, in the financial sector, it's actually been used for decades now, and that use continues. And then it's actually used in a lot of recommendation systems, which some might say recommendations or systems are almost like the backbone of so many online services. And so, things like Netflix and Google, particularly, a lot of DeepMind's work goes into developing and improving Google's recommendation systems. So that's another sort of real world scenario where RL is already being used. It's not something that we really think about or talk about a lot, but it's there. And then another place is a lot of people are now applying it to robots. That's very researchy at the moment. I don't know of a single robot out there that's actively using reinforcement learning, but I expect that to start changing because the results are so like much better than we could have expected. So some examples are coming from OpenAI where they trained, they sort of did this sort of co-simulation where they trained a reinforcement learning algorithm to use a robot hand to sort of solve a Rubik's Cube. It wasn't solving the Rubik's Cube. It knew what actions to take, but it had to learn how to move its fingers. And that was trained first in simulation, which is a game, and then transferred onto a real world robot, and trained sort of further until that got refined. And it created a really impressive looking algorithm, something that is not something that's not very easy to do with conventional methods. And it was also very robust to things like noise. So I hope that kind of clears that up, that there's a lot of avenues for real world application. And because the reason we see games is because at least the current approaches are much more straightforward to apply on games than they are on something real. I think you're on mute.
Thank you. I posted a link to the OpenAI robotic hand that you mentioned in the chat. Also, there's another question if you want to take that really fast, and then we'll move on.
Mm-hmm.
So this person asks, for a high number of input states, E-greedy might even force the model to learn that pain is the best possible outcome for a model to get, as in a 10 by 10 matrix probability to get food is very low if you're computing the max reward in the next 10 steps. Am I approaching the problem correctly?
I don't know if I necessarily fully understand
the question. Yeah, it sounds like basically what they're trying to ask is losing. If you know that you're going to lose, is that ever the right strategy? You just pick you just choose to die as the algorithm. Does that ever happen?
Yes. Sorry. My presentation really should have been titled "Reinforcement Learning: A Story in Pain," or an experience of immense pain. Reward and how the reward is shaped is very important, and this sort of ties to exploration as well. And it is possible to latch on to degenerate strategies, where the model sort of learns to do the least painful thing because, hey, I'm going to die 10 steps from now, so I may as well die now. But the fixes for that, first of all, the fixes for that is you can sometimes change the reward structure. For a much larger grid, the amount of pain for every step would be lower, or in some cases, you can change it so that as the snake gets longer and longer, the pain of existence becomes smaller and smaller, and that negative reward becomes smaller and smaller because we expect it to have to take a longer route. There are other cases where you don't actually use the constant negative reward, and instead use a sparse negative reward. So the snake could have something like a stamina. So it has, it needs to find the next food in n by n steps, where n is the size of the board. And if it doesn't, then it dies and it gets the reward of -1. That's sometimes a useful strategy in situations like that, so that it doesn't learn that, hey, by the time I take the next 100 steps, I'm already going to have a reward of -1, so I may as well just give up. Another way of mitigating some of this, especially along long time horizons, is to use something called a discount factor, where you don't just look at the max Q value of all the future steps, but you're looking at a discounted max future Q value. So something that happens 1,000, 2,000, 3,000 steps down the line actually has a very small impact on what you're going to do now, because that reward sort of recursively gets discounted through the Bellman update, and that sort of punishment doesn't show up as much as the immediate future reward that you're going to get.
Cool. I have a question that's kind of tied to this. Could reinforcement learning algorithms learn to optimize for pain in the short term so they can get a bigger reward in the long term?
Yes, and that's the
we don't have to get into this.
I think that sort of the general answer is yes, but a lot of it comes down to the specific problem. So in the case of snake, excuse me one moment. In the case of snake, you're essentially doing that, right? When you have to take a really long route to get to the food so that you don't die 3 steps from now, it's essentially doing the same thing. But beyond that, I think a lot just comes down to the dynamics of that specific environment and the reward structure that's being used.